Okay, so today's talk is by Valerio Proietti. His title, as you can see there, is Non-Ample Groupoids, Homology, and Smale Spaces. Please, Valerio, go ahead.
Thank you. Okay, thanks for the introduction. Also, thanks to the organizers for inviting me to speak. I've actually never been to Argentina, but it's on my list, and I'd love to come one day. For today, okay, so first thing I should say is that the results I'm going to talk about are obtained in joint work with Makoto Yamashita from the University of Oslo. And so, okay, you can see from this title that there are three parts. So I'm going to remind you a little bit about groupoids and what it means for a groupoid to be ample in just a minute. I suppose homology is more or less familiar to everybody, at least in some vague sense. But I don't expect you to know what Smale spaces are, and so I'm going to spend some time giving you many examples of Smale spaces to convince you that these are interesting things to look at. So, okay, so that's the outline. So as I said, so I'm going to give you many examples, and I'm going to try to connect examples to like different kinds of mathematics. Because Smale spaces actually have many connections, interesting connections to different fields. So, you know, it can be something symbolic or combinatorial, but something like, geometry, foliation theory, also number theory, group theory, and like self-similar actions of groups, and so fractal theory. So there are many interesting connections. This is not like a small class of objects. It's actually quite large, and it's interesting. And also the sister algebras that arise from Smale spaces also form a large class. So I'm also going to explain what the homology groups of Smale spaces are. So there is an ad hoc definition given by Ian Putnam, which uses dynamical systems theory. But then Smale spaces also give rise to groupoids, and so there is also a homology theory just for étale groupoids, which is developed by the community which looks at classifying space of categories and topos theory, and they have a well-established machinery for homology and what it means in terms of also resolutions and stuff like this. And so the point is to compare these two theories to derive some corollaries, which is the third part. So I'm going to just explain two of them. So something about products, so some kind of Kunet formula, and something which resembles Poincaré-duality. Then the last part is maybe the most important result, is K-theory approximations results. So in particular, we're interested at proving that the K-theory groups of Smale spaces have finite rank. This is a conjecture that was, in a paper it appeared in 2017, but in general in this community, it's something that everybody believed. And well, now we have a proof for it. Okay, so briefly, so a groupoid is essentially at the same time a generalization of a group and an equivalence relation. And a compact way to say this is some small category with invertible morphisms. So small here is a set theoretic limitation that doesn't matter for us. And so we talk about morphisms as arrows and the objects of this category as units. And also over an object, there is an identity arrow. So we usually identify the object with the identity arrow, the unit over it. So this would be a discrete groupoid, but we're interested in topological groupoids. So essentially, we put a topology on the arrow space and on the unit space in such a way that it's compatible with the groupoid operations. And then given an arrow, the arrow goes from some object to another object. These are called source and range. So it gives us maps from the arrow space to the unit space. And so a groupoid is étale if these source and range maps are local homomorphisms. And a groupoid is ample if the unit space is totally disconnected. Now you see, if you have a group, you can think of it as a groupoid with one object, and in particular, its unit space will be discrete, so totally disconnected. And so ample groupoids are as close as you can get to discrete groups in a way. And this ample condition can feel very restrictive because, well, if I ask you to think about the topological space, I don't think your first example would be totally disconnected. These are, after all, a little bit counterintuitive as spaces. So if you're not familiar with them, you can think of the traditional Cantor set construction. So, you start with a unit interval and remove the middle terms. And this is a compact example. And so this is an uncountable subspace, but it does Lebesgue measure 0. So in some sense, these spaces have some interesting features. But although this can be restrictive in the theory of dynamical systems, it is actually very common to study a given dynamical system by mapping onto it with a totally disconnected system. And so somehow this tension that lies in the nature of ample groupoids is what makes them interesting. So on one side, they're easy or tractable because they are as close as possible to discrete groups. But on the other side, they're also, from a dynamical viewpoint, they are kind of universal in some sense. Not exactly universal, but like they map onto many dynamical systems. And so we can use them to study even things which are not themselves totally disconnected. So in particular, one thing you can study is this class of dynamical systems, which are Smale spaces. And so the definition of a Smale space is a little bit opaque. So I'm going to give you a vague definition and then several examples. So you can think of just a compact space with some self-map, so some dynamical system, and it's hyperbolic in the sense that somehow the dynamics gets decomposed into two directions, one onto which the dynamics expands, so the distance between the image of 2 points is larger than the image of the points themselves, and on the other direction, the dynamics contracts. And so the stable and unstable directions, they form two foliations, which sort of foliate the space, and they are transversal, meaning that locally they provide us with axes to give coordinates. So locally, a Smale space looks like a product of its stable direction and the unstable direction. So that's kind of the general idea. So some hyperbolic dynamical system with two foliations that are. So, I mean, it's pretty clear. This is, I guess, a very standard construction. Once you have foliations, you have equivalence relations, and in particular, you have groupoids. So the equivalence relation is just that 2 points are equivalent if they lie on the same leaf. So for a Smale space, there will be two groupoids, one for the stable foliation and one for the unstable foliation. So that's how we pass from Smale spaces to groupoids. And so the motivation for this work is dynamical systems, but most of the results, they just hold generally for étale groupoids. So if you don't care about dynamical systems, it is still, I guess, interesting if you just care about groupoids as objects themselves. But okay, so I actually like dynamical systems, so I'm going to give you now several examples of Smale spaces, trying to sort of building up the difficulty. And I'm going to start with the most basic one. So if you have a finite directed graph, you can consider this space of essentially infinite paths on the graph. So the terminal vertex of an edge coincides with the initial vertex of the next edge. And these are dynamical systems because you can shift a path, say, to the left, and that's a self-map. There's also a metric, which essentially says that two paths are distant less than 2 to the minus n minus 1 if they coincide on some interval symmetric around 0 of length of radius n. And so in particular, the distance, when the distance is half, it means that the path they coincide at 0. So at time 0, the path goes through the same edge. And so if at time 0 they go through the same edge, we can glue them. And we can make a new path, which I denote here with this bracket. So I'm gluing the past of F with the future of E. And this is a new well-defined path. And so here you can see that this is a Smale space because, well, it's a compact space. And locally, so when the distance is less than half, this is the Smale space constant. At this scale, I can realize every path as a product. So in this case, it's got E and F.
Sorry, I have a question. So this is order sensitive, right? I mean, how do you know that you're going to put the e's, take the positive part of the e's and the negative part?
Sure.
Yes.
Yes. So yeah. So for the hyperbolicity part, I want to be a little clearer because in this example you can really see it well. So let me be even more concrete. Just take the simplest graph, one vertex and two edges. So at time 0, you can either go through A or through B. So then sigma, this space of paths, will be this joint union of two clopens, one in which the paths go through A at time 0, one they go through B at time 0. And so you can see that each of these two clopens, they have a product structure, because when I am inside one clopen, I can always glue this using the bracket, and every path is some bracket. Now for the hyperbolicity condition. So let's look at this picture. So here on the left, we got two paths, Z and Y, and they belong to the clopen where at 0, they go through A. So notice that, so these two paths, they lie on the same vertical line, which means that they share the future coordinate. So they are the same in the future. In particular, at step 1, they go through B. So I labeled the future coordinate B, E2, E3. Now, I claim that these two paths, they lie on a stable foliation. So that means that when I apply the shift map, they should get closer to each other. The distance shrinks. And that is true because now if I shift these two paths to the left, so time 0 becomes time -1 and time 1 becomes time 0. So you see on the right side of the image now, at time -1, I got A, because before it was at 0. And at time 0, now I got B, because before it was at time 1. So now sigma Z and sigma Y, they actually coincide at time -1, time 0, and also time 1. So the distance has shrunk because shrunk. So the distance is in such a way that if they coincide on larger intervals, then the distance is smaller. So analogously, if they were lying on the same horizontal line, then the shift map will put them further apart. So you can see that in this example, the local structure is Cantor set times Cantor set. So this example is actually totally disconnected. And so these are called shifts of finite type.
Little question. The fact that you drew an arrow with a sigma on top, right? Do you mean that sigma always maps the left square to the right square, every point of it? Because
yes,
it's A. I mean,
yeah, so in this example, I mean, you are correct. So in this example, we are thinking where essentially we use the shift map on these 2 points. But if I have something like A, this is when I shift, this is fixed, right? So it doesn't go on the other side.
Yeah, but it can also be that, I mean, you can get from one to the other, but not with just one application of sigma, but several. Right?
Sure. Of course, the constant A, you will always see A.
Yeah, no, but if you have, I mean, 4 A's and then a B, then
of course.
Yeah. Okay.
Yeah. So I mean, of course, this is a little bit of a simplified picture, but of course you're right. So essentially, okay, so this example is important because it's the most basic one in a way. But let me show you an example which is more maybe more related to geometry. So this is actually an Axiom A system, like Smale defined them. So in this case, you take a solid torus, and then you consider a smooth embedding of the torus into itself. And essentially, so I give you a formula here, but the formula is not very important. So what this map does is essentially it stretches the torus in the longitudinal direction, and then it contracts each sort of a transversal disk, and then it wraps this torus sort of twice, and then it puts it inside T itself without self-intersection. So this is a little bit of a mouthful, but there is a nice picture. This is what the map is doing. So here I'm applying the map 3 times. And so you see that if I keep applying the map and then I consider the sort of nested intersections of all these, I will get some invariant system. And you can also see somehow that this system will look a little different than before, because it looks like in one direction the system will look like R, and in the other direction the system will look like a Cantor set. So the R direction will be essentially the longitudinal direction, and the Cantor set will be given by essentially when I cut the solid torus meridianally. So on the first step, I see 2 disks, then I see 4 disks, and then in the limit, I would see a Cantor set. So yeah, so this slide essentially says in word what I said. So you can consider this intersection. This is the this is called essentially the basic set of an Axiom A system. You can present this also slightly easier without starting from a solid torus. You can just start with a circle and the squaring map and take the projective limit of this, and that will give you a space which is homomorphic to lambda, and then the squaring map on the coordinate wise will have the same effect of the map phi above that I explained. And so the local structure is R times Cantor. So here's another example where there is a little bit of number theory going on. So of course, I'm just giving you some details and simplifying things a bit, so I can't really go into, I can't really tell you whether this has actually, it's not a number theory talk, but at least there are some objects that appear that it look like they would have some application in this direction. So here, okay, we consider the p-adic numbers and the q-adic numbers for p less than q primes. And then we consider this map on qp times r times qq. So it multiplies by p inverse q. Essentially, by the definition of how the p-adic number works, we have the p inverse expands and q is in a symmetry. And then on the real line, q mod p expands because q is bigger than p. And then, okay, dually on the q-adic numbers, you got that p inverse is in a symmetry and q contracts. So the space is not compact, but there is an invariant lattice, which is z extended by 1 over pq. And so, f is still well defined there. So if we take this quotient, we give a compact space now. So that's a Smale space again. And here the local structure is R times Cantor times Cantor. So slightly similar to the one before, where we have R times Cantor, but with an extra component. Okay, so there's other examples. So there's one that I enjoy particularly from self-similar actions, but they're more technical. So let me just give you one example where it looks like there is no totally disconnected space inside. This is also fairly easy. So you pick a matrix which is hyperbolic. So that means when I diagonalize it, I get so an eigenvalue bigger than 1 and 1 smaller than 1. So here I choose the golden section. And then, so this matrix, okay, so determinant 1 is integrally valued. So it gives me a map of R2 mod Z2. So it becomes a hyperbolic toral automorphism, so of the torus. And then, of course, you can see that this is going to be hyperbolic, right? Because when I'm away from the boundary of the fundamental domain where the gluing is happening, essentially the coordinates are given by the lines spanned by the eigenvectors, which are given by B. And on those lines, I will have expanding and contracting behavior. So this is the picture essentially. So away from the gluing, you can pick some neighborhood where the eigenlines will give you some axis in that way. And so here, the local structure is R times R. So there is no total disconnectedness. And there's plenty of examples of this kind. And now the point of the title, when I say non-ample groupoids, I mean, I guess technically I should have said not necessarily ample groupoids, is that there are dynamical systems for which you can't reduce the situation to an ample groupoid, but they're still interesting. For example, the sister algebras associated to this Smale space, the one showed here in the picture, is essentially more equivalent to the rotation algebra, which clearly is an interesting example, commutative geometry. So you want to be able to encompass those from the point of view of homology. Okay, so briefly, I'm going to explain now how to define homology for these Smale spaces. So if I have a surjection between Smale spaces, which is compatible with the dynamics, I call it S bijective if it is essentially, it preserves the stable sets. So it's a local homomorphism of the stable direction. And of course, it's going to be U bijective if it preserves the unstable direction. Now, one thing that you should remember for this talk is this notation. So sigma is always some shift to finite type. So this is some totally disconnected Smale space. And phi is a map which is an S bijective map from sigma to some space X that I want to study. So X is going to be always the space I want to study. Sigma is always going to be some shift to finite type, and phi is going to be some surjection onto X. So here I give you an example where sigma is the full 2 shift. So that's the example from the first example. And X is the solenoid example of the solid torus. And in this case, the S bijective map can be actually written explicitly. It's written here. And okay, so the analytic precise form doesn't matter, but essentially this is sort of like the binary coding of a unit interval. Or this is kind of an elaboration of that. In particular, this map is 2 to 1. Okay, so this is, as I said, like a standard technique in dynamical system. So this map phi, in some way, you can think of it as a symbolic coding of X. So X is not necessarily a symbolic object, but sigma is. And so we want to study X by using sigma, because sigma is simple.
One little...
So,
yeah, sorry to interrupt you.
No.
So could you explain, I forgot already what elements in the dyadic solenoid look like. So would you explain how this phi E lives in X? I mean,
yes.
do you differentiate
essentially, so the points in X, they are essentially the projective limit of the squaring map of the circle. So they are sequences of circle points.
Mm-hmm.
So there are sequences of circle points satisfying the projectivity condition. So it's an inverse limit of spaces. And so, being sequences, I have this index n on phi E n. So the n component of the sequence in X will be this point of the circle. So this is, exponential of 2 pi I something. So it's going to be something in the circle. And essentially.
But isn't EK minus n an edge in a graph?
Exactly. And it is the full 2 shift. So the edge are 0 and 1. I called them A and B before. Okay, I think this is where your confusion comes from.
Yeah. I thought yes. the name of the arrow of the edge. So
yeah. Of course. Yeah, no, I understand, yes. So each E sub K is either a 0 or a 1. So like either an A or a B as before.
Okay.
So it's literally the binary coding of the unit interval. And then, you play around with this a little bit more and you get this. So one key thing that Putnam did was kind of refining this idea of symbolic coding over a space. So in general, for a Smale space, this is not good enough. What you need is not a map phi, but you need a diagram phi, as in the bottom of this slide. So you want to study X, and you find 2 spaces which map onto X. They are not necessarily shifts of finite type, so I do not use the letter sigma, But so the one on the left maps S bijectively, and the one on the U maps U bijectively. And then the interesting thing is that now I can take the fiber product of Y and Z over X, and this is going to be a shift of finite type. So in some sense, I turned this map phi into a two-step process where I first disconnect the stable direction, and then I disconnect the unstable direction. So in the future, I will have slides where I will use phi and sigma, and sometimes I will cheat. So the point is that in general, you need to use this diagram. It's not enough to have just one map, but you need to use these two maps. But okay, so the notation sometimes gets very complicated. And so in certain slides, I will sort of pretend that I'm in a simpler situation where one map is enough. But the whole thing can be done using two maps, and this is actually the whole point. But so as you can see that somehow this becomes very difficult notationally, because if one map gives you a chain complex, then two maps will give you a double complex. And sometimes we need to consider double complexes which have also a third direction, so they have like tri-complexes. So then somehow the indices problems become a bit difficult to just put on a slide. So just a warning that sometimes I will sort of pretend that I have only one map. Okay, so let's remember that I have this space X I want to study, and then there is some map phi or some diagram phi with Y and Z, and their fiber product is sigma, a shift to finite type. So that's what it is. So I have this fiber product, that's a shift to finite type, and then I can start taking the iterated fiber product, and I get the sigma i's. And so this would be now a simplicial space. And so once I have a simplicial space, if I have some kind of functor to abelian groups, I get a simplicial group, and so a chain complex. And so, of course, then the homology would be the homology of that chain complex. And so there is some work to do to show that somehow the homology doesn't depend on phi, so the diagram I started with. And also, I need to tell you what is this functor ds, so this functor from shifts, so from the sigmas to abelian groups. And I'll tell you that in a little while. But essentially, the definition is this. I start with a Smale space. I come up with some diagram, which I think of as some resolution. And this will give rise to a simplicial space. And then I have some prescribed functor to abelian groups. And then I will take the homology of the corresponding simplicial group.
So for you, shifts of finite type have trivial homology.
Exactly. They will have only H0. That's right. Okay, so I said that given a Smale space, I have some groupoid or other actually an equivalence relation. And I said that it's essentially given by lying on the same leaf. So one maybe better way to say it is this. So X and Y are, say, unstable equivalent if essentially in the past they get closer and closer. And of course, for stable equivalent, I'll look at the future. So this will give me an equivalent relation, locally compact and Hausdorff as a Hart system. But actually, I want an étale groupoid. So here is where I need to essentially reduce the groupoid to a transversal. This is also a standard technique in foliations. And once I do that, I can essentially reduce my groupoid to a smaller groupoid that I can sort of retopologize with a slightly better topology, which makes it étale. And this operation essentially leaves the groupoid invariant up to Morita equivalence. So this is a technical point, and from now on, where I say RUX is the equivalence relation of a Smale space, I will always assume that it's already étale. So here's another piece of notation we need to remember now. So I have this X and this phi and this sigma. And now I have RU. So this is the unstable equivalence relation of X. So some groupoid attached to X. And when I say sister algebra of a Smale space, what I really mean is always the sister algebra of this groupoid. And of course, it's going to be two, one for the unstable groupoid and one for the stable groupoid. Okay, so I said that I need this functor to abelian groups, and I called it DS, but I didn't say what it is. And in some sense, I will never tell you what it is, because I can describe it in other ways. For example, I can use K-theory. So for a shift of finite type, this groupoid RU is AF. So the sister algebra is also AF. It will have odd K-theory 0, and even K-theory will recover this invariant DS. So you can take this as a definition. Another point is that when I have some S bijective map from two Smale spaces, say from Y to X, this always gives rise to an open inclusion between their corresponding equivalence relations. And so this is actually quite important, because when you import this observation in KK theory, you can essentially do induction restriction. So, I can view RUY as an open subgroupoid of RUX. And by using induction and restriction, I can construct projective resolutions in equivariant KK theory. So this is important to construct approximations of K theory in combination with the bound-Kohn conjecture. So I won't say too much about this, but yeah, please.
One little question. Is your DS group somehow related to, at least in very particular cases, Krieger's dimension groups?
It is exactly Krieger's dimension group.
Okay.
Yes. Yes, it is. In fact, I mean, this is in that form is how it appeared first, and later it is observed that it's also a K-theory group and other things. Okay, so I have to say a few things about homology for groupoids, and I need it in some form of generality. So I cannot just consider sort of integral coefficients. I need to consider homology for equivariant sheaves. So, okay, so what is a G-equivariant sheaf? It's essentially just a sheaf over the unit space of the groupoid, plus some isomorphism between the pullback of the sheaf over the source map and the pullback of the sheaf of the range map. So when you have a sheaf, you can always pull it back. And this is similar to essentially, in a way, what is a G C-star algebra for a groupoid. It's some kind of fibered object over the sort of upper semi-continuous C-star bundle, so fibered object over X with some kind of isomorphism, which sort of tells you how to go from one fiber to the other. Okay, so I have this fact here, which is to support one of the things I said at the beginning, that ample groupoids are more tractable. So if you don't like sheaves, then as long as you stick to ample groupoids, you're in luck, because in this case, instead of thinking of sheaves, you can think of G sheaves over an ample groupoid as unitary, essentially, modules over the completely supported functions from G to the integers. So there is a correspondence. So this is one reason why, if you deal with ample groupoids, somehow things are a little easier, because you can just stick to modules instead of sheaves, and this can be easier. So, okay, we need to somehow construct resolutions of sheaves, and we are happy with C-soft resolutions. So that means that if I have a compact subspace, I wrote closed because I'm still thinking of ample, but it should really be compact, K in Y, and some section, then there is a global section whose restriction is S. So this is, I think this should be ring familiar with when we deal with, the theorem cohomology, and we want to prove that the theorem cohomology is also sheaf cohomology for stuff like this. Okay, so now I have the sheaf F, and I construct a C-soft resolution. So this is possible. I can always essentially look at the Flaby-Godemont resolution, the canonical resolution, and I can truncate. And I can truncate essentially because I'm always assuming that my space X has finite cohomological dimension. It's not like some kind of infinite dimensional manifold. This is, I don't want. Okay, so inverting the degree, I have this bounded below chain complex. And then the homology of B with coefficient in the sheaf F is this hyperhomology. So it's a fancy word, nothing too difficult. So essentially what I do is that I need to, in some sense, take a bicomplex. So in one direction is given by S dot, and the other direction is given by the nerve of G. So here I have G2, G1, X. So G2 will be the pairs of arrows which are composable, and Gn will be the sort of n tuples which are composable. And so essentially the nerve of G and S dot will give me two directions and will give me a double complex. And the homology of the total complex of that complex is the homology of GF. So here is the bar resolution of G. So this will give me the other direction. So the first one was given by the resolution of the sheaf. So this one is very simple. If I have n composable arrows, I can compose two of them and I get n minus one of them. And then for the edges, I can just remove them. And for one arrow, I can take source and range. So this is pretty standard. It's more or less how you construct the classifying space of a discrete group. Okay, so now for the comparison. Okay, so first we have another observation. So we have this Krieger invariant that this is DS. And we said that it's also the K-theory of some sister algebra. Well, it's also the degree zero homology of the groupoid associated to a shift of finite type. This shouldn't be too surprising. And also, as we already remarked from one of the questions, the higher homology is zero. So this is good because in some sense, if I have higher homology zero, I have some chance to get some kind of acyclic resolution, which is usually good enough to compute homology. So the idea is like this. I have this X Smale space I want to study, and in particular, I want to study Ru of X, so the groupoid over X, and I have some sheaf over it. Now, if I start with my map phi, mapping from a shift of finite type, now, okay, this should be a diagram, but okay, just bear with me. It has bijective. Then I can consider these functors. So one is pull back, and one is push forward with a shriek. So this for spaces is more or less what you imagine, and for groupoids, it is slightly more complicated. Now, under some assumptions, this is an adjoint pair of functors. Even when it's not adjoint, we can still use this to construct a resolution. So maybe we should just think that there are adjoints. And essentially, so this is also pretty standard. Somehow, when you have some kind of adjunction, it gives rise to a comonad, so some kind of endofunctor with multiplication and unit and co-unit. And so you can use that to construct a resolution.
You mean, do you not define phi lower shriek as the left adjoint of phi star?
No, so you can define it just with a certain definition, and then you can prove that it's adjoint. So essentially,
when it's not the adjoint, is it because adjoints don't, I mean, some limit or colimit does not exist, or just a failure of the definition to be the adjoint one?
Yeah, so in some sense, it's more like a failure, like you said. So, so the correct hypothesis is that, so if, how to explain? So if your map phi is somehow Moride equivalent to the projection from a sort of transformation groupoid. So say that I have some groupoid G acting on X, I can make this new groupoid X cross G. And then there is a groupoid map from X cross G to G itself. So this I call the canonical projection. So if phi is in some sense Moride equivalent to this sort of form, then I have an adjoint. So this is a concrete criteria.
Okay.
And so in some sense, it has to do with a certain pullback. So as you said, some kind of limit problem. Okay, so essentially you get this now augmented simpliciter sheaf over X. So I can just pull back and push forward and do it many times. And this is some augmented system over F. And eventually you want to prove that this is a resolution of F. And so in some sense, you want to use this proposition above. So you want to say that this is acyclic, so it will give you a resolution. And so if you do it for the integers, then of course the pullback is going to be also the constant sheaf of integers. And so how do you show that it is an acyclic resolution? Well, essentially, there's two things you need to prove. Well, the first is that if I do now the homology of Ru of X with coefficient of phi shriek of F, then this is the same as the homology of Ru of sigma with coefficient in F. So this is essentially coming from a certain spectral sequence that's collapsing. And now the final remark is that, so remember my homology was defined as a fiber product, an iterated fiber product of different sigmas. So in some sense, I need to study how the shriek and the upper star map, how they behave with respect to fiber product. This is a sort of change of base theorem. And so there is this formula here where you should think of this as a quasi-isomorphism. So using this, I can get to prove that essentially the homology of Ru sigma n, so the iterated fiber product, is obtained as the homology of Rux on the n iterated, of the n degree resolution that I have. So this phi shriek phi star of the constant sheaf of integers. If I do this, the bar complex direction gets collapsed because I only have homology in degree 0. And what remains is the other direction, which is by definition Putnam's complex. And so essentially what you proved is that the homology of X defined as in Putnam's definition is the same as the homology of the groupoid in the sense of equivariant sheaves. This is true for any non-wandering Smale space. So non-wandering is a very mild hypothesis. It's essentially satisfied by all interesting Smale spaces. In the sense of Axiom A system, as Smale thought of it, or Anosov, it essentially means that the periodic points are dense in the space. But remember, we don't care about the periodic points for the map because we actually care about the foliations that the map induce. So we don't care about the orbits of the map itself. We care about the foliations that the map induces. So this periodic dense is actually totally fine. So the argument that I just gave, essentially, as you saw a little bit, I cheated a bit because I was using phi as a map rather than as a diagram. In general, you have to, instead of having a bicomplex, you have to go to a tricomplex. You have to consider sort of a U bijection in addition to an S bijection. And then you have a tribal complex, and you can do the same argument, it just gets more complicated. So essentially, you will have three indices, one which controls the adjunction, one controls the nerve of the groupoid, and one controls the U bijection that you're adding to the diagram. So one corollary that you get from this is the Kunet formula. So the Kunet formula for Smale spaces holds just because it holds for the groupoid homology. And then you also get a Poincaré-duality theorem. And it holds for Smale spaces whose unstable foliation is homomorphic to Rn. And of course, to make it hold, you need to, so here I have the homology of Putnam in degree k with the cohomology of n minus k, where n is the dimension. And the sheaf I need to put is, of course, so I have this double orientation cover, and I'm twisting the constant sheaf of integers with this orientation sheaf. So this is analogous to what you would do with just Poincaré-duality for a non-oriented manifold. So more generally, this doesn't just hold for Smale spaces, it holds for any groupoid such that essentially the space of arrows for lying on some point X is homomorphic to Rn, and that it's essentially Morita equivalent to some étale groupoid. And essentially the same result holds. Okay, so I will be a bit brief on this. So this Poincaré-duality, it holds for substitution tiling systems. It holds for the toral automorphism that I gave you before. So here I have an example which I didn't introduce, so I'm going to skip this part. And it also holds for infranil manifolds, which are essentially generalizations of this hyperbolic toral automorphism that you have. Yeah. So this is this duality is useful because, well, it allows us to compute homology of a groupoid as just as cohomology of some space, which is much easier. I mean, we have more tools. Okay, so as I said, I'm going to skip a little bit of details on the examples, but there are more examples essentially. Just the problem is to introduce them. Let me just get to the last part since I have 5 more minutes. So the last theorem I want to prove is something about K-theory. So as I said, it says that the K-theory of this Smale space sister algebra is finite rank. Okay, so a good way to prove this would be to essentially relate the K groups to the homology by some spectral sequence, and then tensorize with Q, and use the fact that the homology has finite rank, and conclude that the K-theory has finite rank. This is actually possible if the groupoid is ample. But so the whole point is that we're going beyond the ample case. So we can't have this direct argument like I just explained it. We actually have to sort of connect 2 spectral sequences. And so this corresponds to the idea that if I have a general Smale space, as I said, I am doing this 2-step resolution with this diagram, one from the left and one from the right. So I will have, in a way, 2 spectral sequences, which sort of talk to each other. And by combining them, I can still get this finite rank. It would be nice to have a 1 spectral sequence. And I don't know if this is possible. We can't prove it yet. But at least this finite rank idea still works. So I'm going to give you just a few ideas of how this works. And so as I said, essentially, you do one case for the stably disconnected, and then you do another case for the unstably disconnected, and then you combine them. So let's look at the unstably disconnected case. So if I have some symmetric simplicial space, so just some simplicial space with compatible action of the symmetric group, I can construct some geometric realization, which I call naive. So essentially, it's going to be just the quotient of the geometric realization for getting the symmetric group action, quotient by now the diagonal action of the symmetric group on the simplex and AN. So now, if I have some locally compact space and some proper continuous surjection by T0, I now take the n+1 fold fiber product, and I get these TIs. And of course, these TIs, they form a symmetric simplicial space, right? It's obviously symmetric because I can just swap two points and they will still map onto the same point, so in the fiber product. So I will also have to suppose that D is at most n+1 for some n. And what you get is that, so there is a proper surjection from this naive geometric realization onto the original space T. And now you have this so essentially approximation or recover of cohomology and K-theory, topological K-theory results, where instead of dealing with the T space itself, you deal with this geometric realization. So we now apply this idea equivalently, and I'll stop there. So here, it's actually important that the groupoid satisfies the bound-Kohn conjecture, and it has torsion-free stabilizers. So this is because in this case, I have some spectral sequence that I can use. And so the idea now is that you do the same decomposition of T, but you do it equivalently. And so now you will get some kind of map from the unit space of G to this naive geometric realization. So think of C star G also as a cross product, but a cross product over T. So the unit space is T0, if T. And so what you see is that this still works. So if you use the spectral sequence, you can prove by comparing spectral sequence that the K-theory of the groupoid sister algebra is the same as the cross product of G acting on this naive geometric realization. So what did you gain with this? Well, you gain that now the naive geometricalization has a skeletal filtration. And so you can use, for example, the work of Segal. So you set up this E1 page where you take essentially the difference of P skeleton, P minus 1 skeleton. And this will give rise to some spectral sequence. So, okay, so here, of course, you need to work a little bit. You need to be careful of exactly understanding what this different space is. And here I have a little sentence explaining that it has something to do with the union of the free orbit of the symmetric space. Sorry, the symmetric group. And so we get to this final result that, well, so now if I apply this to a Smale space and some U-bijective map, so this would be my Twiddle, and then I have my T. Now I also resolve the sheaf as I did before, and I put this all together, and I can actually prove that these K groups of the sort of skeletal filtration, they are the same as the degree 0 homology of G with coefficient of my resolution. And so if you put everything together, what you get is a cohomological spectral sequence, which is abounding to the K-theory of the sister algebra that I want. And the E2 sheet is given by this groupoid homology. So this holds when X is unstably disconnected. And then you have a similar one, a homological spectral sequence, when X is stably disconnected. So you put them together, and you can essentially derive from here that you get finite rank of K-theory groups, essentially by rationalizing and using that homology of this finite rank. Okay, so that's the conclusion. Essentially, there are three takeaways. So one can use symbolic coding to construct sheaf resolutions. This is a key idea. And this gives us an identification of the homology groups in the way Putnam defined them and in the way they are defined for groupoids. And now you can go further. Essentially, you can try to, and this is really the last part, so you can try to leverage the simplicial or co-simplicial structure that you obtain from this diagram that you start with. So this, it's called an SU bijective pair, this diagram in Putnam's paper. And so you can leverage this structure to obtain K-theory approximation. So one is a finite rank result, is the one I just talked about. But you can also start, I mean, you can ask yourself, okay, so since the sister algebra of Smale spaces, they're classifiable, can they, so it's the range of K-theory on all this Smale space sister algebra, does it exhaust all real rank 0 simple classifiable sister algebra? So this would be quite good because, well, you have this invariant, and so you can say many things. Unfortunately, because we proved that it's finite rank K groups, this is not true. Well, I don't know if it's unfortunate. It happens to be not true because you have, classifiable algebra which actually do not have finite rank K groups. But okay, so this is one other thing that you can, some other question that you can answer in this way. Okay, thank you for listening.
Okay, thank you very much, Valerio. Are there any questions from the audience? We don't see any reactions here. I have some questions. So a very basic one is, when you started the talk, you mentioned some conjecture that you said, and now we have a proof. And so I thought maybe along the talk, you were going to say, I proved this conjecture. But is it one of these contributions that you are describing?
Yes, so essentially, this is the conjecture, is the theorem. So the K groups of any wandering Smale space are finite rank. Sorry, I should have been clear.
Okay. And so why what was it that you said that if it were always in the class of classifiable algebras, you mean stable under the Young?
Yes, so the point is So if you look at the sister algebras on Smale spaces, they are classifiable. And so you can ask yourself, so people have asked, so if I look at the class of classifiable, simple real rank 0 sister algebras, and I look at their K-theory groups, can I exhaust all of these K-theory groups by K-theory of Smale spaces?
I just said no because there are some that don't have a finite rank.
Yes.
Okay. And and is it always is this sister algebra always simple?
So this sister algebra, yes, they are simple.
And
so the point is, I think one of the confusion is that one has a dynamical system, so a self map of a space. You can construct the cross product, right? But so of course, if the self map has periodic points or like fixed points, that's not good. I mean, it won't give you something simple. But so the point is that here these are not cross products, because we actually don't consider the orbits of the self map, but we consider the foliations that the self map induces. So these foliations, they are minimal. So meaning each leaf is dense in the space. So then this geometric condition of the leaf being dense in the space will essentially correspond to the sister algebra being simple.
Okay. So you mentioned several times this, that you're saying that this sister algebra is related by foliation. Is this Cohn's sister algebra or a foliation? It's the groupoid of foliation and the sister algebra of the groupoid.
Yeah, so it can be, but it's not always going to be like that. So essentially, Kohn construction is you have a foliation, you consider the holonomy groupoid. And then the sister algebra of the foliation is the holonomy groupoid sister algebra. The thing about this is that the holonomy groupoid in general can be, for example, non-Hausdorff, or also it can have stabilizers, which are not trivial. But in these examples, these groupoids, they're always Hausdorff and they're free. They're equivalence relations. So in general, there is many foliations that have holonomy groupoids which are not even Moride equivalent to this kind of groupoids.
Okay. And we just and the torsion of these K groups is too complicated. I mean, too out of bounds.
Yes. So the yes, this is a good question. So the torsion is quite difficult.
But can it be infinitely generated, say? I mean, are there known examples where it's not finitely generated?
Yes, I think yes. But so this group did not be finally generated. I would. Well, is that? Yeah. So the point of the torsion is that, well, in a way, this is so these K-theory groups and these homology groups, they are related to this HK conjecture of Matsui. Right. So it's essentially prescribed some isomorphism between the K groups and the homology. And so we know that this conjecture is not correct. And so the most recent counterexample by Robin Dilly essentially is highlighting exactly the problem of torsion. So in general, I mean, even for manifolds of dimension more than 4, I guess, torsion in topological K-theory and torsion in cohomology is distributed differently. So the best you can hope for is a rational isomorphism.
Okay, okay. One more thing, a question of language. When you use the term self-similar several times, I have read about this Nekrasiewicz system algebras and Excel Pardo generalization, and I'm actually writing a paper on these things, but I never understood why they say that this. I mean, you have an action of a group on a graph and a cocycle, and why. I mean, this is called a self-similar action, and I don't understand where that comes from.
I think maybe, okay, so of course it will depend a little bit on the setup that you have. So one easy example from Nekrasiewicz is, so you start with some finite alphabet and then of letters, and then you consider all the finite words. So this will be a rooted tree. So suppose that you have a group acting on these letters, and then it will induce a group action on the words. So, okay, suppose you have a word, say the word friend, the first letter is F. So when you have a G element acting on friend, you will say that the action is self-similar, is essentially you take the G action on the letter F, and then there will be another group element H, depending on G, which will act on the remaining of the word. So on like the starting from R. So this new element, you call it the section of G at F. And so you see the action is self-similar because what you can do is, instead of considering the action of G on the whole word, you sort of you do one step, and then there will be a new group element acting on the rest, and then you can sort of inductively go. So
I know the new group element is given by the cosine.
Yes, exactly. So this section will have this satisfy some cocycle identities. Yes. So in general, once you have this, instead of considering these finite words, you can consider so these bi-infinite paths, like I did on these letters. And then this group action will give you some notion that I think Nekrasiewicz called asymptotic equivalence relation. And so the quotient space, it's actually going to be a Smale space. This is proved by Nekrasiewicz. So it will have hyperbolic behavior and everything. So this is actually another example that I didn't have time to include because, as you just pointed out, somehow the beginning, the starting setup is a little bit, difficult. So it's not completely intuitive to just give an example. Yeah.
Well, okay. So if there are no further questions, and I don't see any in the chat or anything, so I will stop the recording.